Okay. Yeah, let's start today's lecture. So yeah, we talked about transformer. Hold on. Sorry. Okay. So yeah, we talked about a transformer, which is I think we spent a kind of two lectures. One is attention, the other one is a more general transformer. Now we will start moving to the language model of transformer. So today is more of a general overview, and then we will talk more about the details. Transformer-based language models. Essentially, if you recall, we talked about transformer. We have encoder, decoder structure, right? So for the language models, we probably all know the LLMs are decoder only. But before that, there were also encoder and encoder-decoder structure, which is in the LLMs or in whatever the language models. So we will talk about those and discuss a bit the relation and so on. Anyway, so this is a plan. Yeah. So we will talk a little bit about natural language understanding and natural language generation. Traditionally, these are regarded two different topics. Before, like I think, I mean, in the older days, or even until pretty recent, they treat this separately, and this is also distinction of encoder and decoder. If you recall, we have this encoder-decoder lecture, right? Talk about the encoders for representation, decoder for generation. So if you map here, natural language understanding is a more semantic representation type of it's more flavor of representation. So it's kind of associated with encoder. And then natural language generation is more associated with decoder. That's traditionally, but now things change. So we will talk about that. And then there's pre-training and fine-tuning. This was a paradigm, I think, started with, I think it's probably earlier, but around the time after ImageNet. So maybe around the last 10 years, right? So BERT for the natural language understanding was a model which was more clearly, but at that time GPT also occurs. So around those times, this pre-training fine-tuning paradigm is starting to become popular. So that's already nearly 10 years. So at least 7-8 years. Encoder only, this is a BERT, right? Encoder, decoder, this is more aligned with the original transformer structure. So like BART, like T5, and so on. And decoder only, of course, nowadays is all the large language model decoder only. So you don't have encoder. The only thing you see an encoder in the large language nowadays is multimodal model. So multimodal model, you still need the encoder decoder model, right? So, and we will talk about that I actually later on. Yeah. Anyway, so this is about what we want to go over today. Let's talk a little bit about the natural language understanding, natural language generation, and the encoder-decoder view, which go back to our earlier lecture about encoder-decoder. If you recall, we have encoder, decoder, autoencoder, right? So natural language correspond to traditionally encoder. Basically, you learn representations of a text, right? Like classification, sentiment analysis is key. Application, and then you say tagging, right, and so on. So those are the you understand the language. Retrieval related to the embedding. We have talked a little bit about that embedding model, right? So if you recall, when we talk about the embedding model, we have this contextual learning, right? So this is for retrieval. Would be we have the example of that. But typical all those, you know, it's like an encoder. And what's a differentiate encoder and the decoder? It will only one thing. Is one is a bidirectional attention, the other one is the cosine attention. Basically, this is just to refresh your minds. Natural language understand. This is a decoder. If you remember the lecture, right? So that's for generation. So yeah, basically, you know, you just generate a sentence. And translation is typical regarding the as generation, summarization, dialogue, and so on. Right. So those are decoders. Dialogue, of course, very like related to the chatbots, which we are looking at nowadays. But this is right. So basically, you know, this is a picture. This picture reflects the same thing as what we see in the encoder decoder. It's just more targeted towards the text, right? Input text, encoder. This is a little bit more on the, let's say if you ask people 5 years ago, right? So this is the picture people will have. But later we will talk about why decoder only models can handle both. This is come actually with a surprise. This is after ChatGPT, right? So starting that is probably 2022, 2023 already. At that time, you know, people realized the decoder model can. Actually, GPT-3 itself, there was it was the newest best paper. I think it's 2020 or 2021. That's already has this flavor. We'll probably say a little bit about that. But essentially, you know, we will have why this happens. But anyway, so that's the traditional view. So we will starting with this view. And the encoder is still useful, by the way. I mean, it's not say it's not useful anymore, but you know, it is useful. Internal omni transformer. Recall that the only thing you differentiate is one is the output is the hidden state, right? It's not the next token prediction. You don't predict the next token. It's just hidden representation. It's a transformer layers. The top transformer layers output will be your encoder output. But from implementation perspective, you just remove the hats. That's all, right? You just remove the this logic generation side, but the real part is it's a bidirectional attention. That's I'm just keep mentioning this just so that we all know that you know this is the key differentiation about the encoder and the decoder. Encoder omni model use bidirectional text, and this is why when people talk about BERT, they're easy, they're good because they say they're bidirectional. Right, you can attend, so you know the information from both, not just one direction. This is useful for classification and so on. So, decoder omni model. I mean, of course, that's LLMs, right? So all the LLMs are decoder omni model. It just attend to the left, and eventually it also output the next token, right? So in the here is a one is output. The next is always the next token prediction, which we talked about before. So we don't have to look much more to that. Okay, so this is essentially about these two models. This one just a refresh mind, and then we basically map that to the actual model. Now let's say, yeah, this is basically auto-regress. Right? So basically, yeah, we know that we already go over that, so we don't want to say more about this. There's also, of course, encoder decoder. And again, encoder decoder is the original transformer papers model. And that's an encoder decoder model, right? So basically, the idea is you have input text. It's a think about translation. It's a or summarization, right? You have one input text, which is the source language, and you have bidirectional attention in the encoder. Cross attention to every token here for the top layers of encoder. as your information to say how do you utilize the input data, and then you have a causal attention in the decoder, right? So basically, this is the picture what we have shown before, and this there's T5, Google's T5. It's still you can download that now, and BART would be regarded as a representative examples of this architecture. And they are also used. The idea of that is, why Google Google actually spend now they have Gemini and so on, right? So, but before that, Google spent quite a bit of time on the encoder, which is BERT, was Google's model, and the T5 was encoder decoder. They are coming to the decoder only later. So, but they have a lot of work in the encoder and the encoder decoder model. So basically, this is the original transformer model, and the idea is encoder is a better representation of your information because it's a bidirectional attention, and the decoder can be actually used to generate. So it's somehow the claim is the best of both worlds, right? But in reality, there are some complications. So yeah, employ a dual architecture, right? So each perform cross attention and so on. So this is again something we know, and the thing is why that, right? So basically, okay. So basically, these three architectures we both have appeared in recent time. The real models they try to do the natural language, right? Now let's say why decoder now suddenly becomes dominant, right? So nowadays, I think they still exist. You can still use that BERT like that, but they are not actively developed. You just use what's there available, right? There are usually small models, encoder models. Very difficult to train larger models, and usually it's but still they are useful. For example, you can use a BERT for classification, right? Still, it's a small model, and then it's okay. So it's good for NLU, right? Encoder, decoder, good for sequence to sequence, right? Sequence like translation, right? So this GPT good for natural language generation. So this is traditional, but now everything is coming to here, right? Of course, why is that? Because the key idea, the main key is it's easy to train. One thing is it's much easier to train a decoder. For example, given your English text unlabeled, how do you train an encoder decoder model? Or how do you train an encoder model? Actually, encoder model is we will talk about that, how you train. But the encoder decoder model, somehow there's no clear separation, right? Usually you have to separate the source and target language, or at least source sentence or target sentence. It's not very natural. Decoder, you don't need to worry about that. You just train whatever is given to you. So that's much easier. So that's actually, it's very important when you do the large scale training using internet data. It's a unified interface. It's a simplify a lot of things. Even talking about nowadays people moving to the agentic right settings and so on. They can use agents and so on, but you will realize everything can be encoded into the next token prediction, no matter what you do. So that's actually is not being recognized before. People know that. Of course, mathematically you can say that it's always possible, but practically people didn't realize it's powerful enough. With a prompt plus word context, right, plus your generation will be sufficient to solve all the NLU. This is something, right? Basically, prompt is another. And prompts for doing this one and starting to explore GPT-2, GPT-3. Mostly starting from the GPT-3, they're starting to be realizing the prompts. At that time, there are people starting to looking into the prompts and try to play with natural language with different prompts, starting to do that. And then actually this is something I think OpenAI started pioneered on this, and then they demonstrate that actually using prompts, you can basically turn an NLU problem into an NLG problem. So basically, you just keep generation. That's all. So this is I think because of those, there's nothing, especially it's hard to train for the encoder. Also, it's much limited because next model generation, this is very unified. You can do essentially everything by just treating that as nice token. So that's another thing. So okay, so few shots learning is coming from GPT-3, then that newest paper, and they talk about, but that one we'll talk about later. When we see. This is just in context learning. You can have a lot of contextual information to give you decision power of the LLM. Now, the modern framework to train this kind of model, right? All the model we talked about, like BERT, like BART, like GPT, they are all pre-trained models. So what does that mean, right? There's a paradigm which started around 10 years ago, probably it's 8 to 10 years ago, and clearly starting from BERT and the GPT-1. At that time, they pushed to this unsupervised pre-train. So you start with unsupervised pre-train, right? And then you can say, okay, what is a model? Your model, you can do the supervised fine tuning. This is encoder-based model, right? It can be encoder-decoder model, can be decoder-only model, right? And then you go through the supervised fine tuning. Then you go through application. So that's basically the paradigm. And we will talk about this more later on about this. And essentially, the original is slightly different than current, right? Current setting is once you train this model, after you still, this is usually called pre-training, right? So unsupervised pre-training. This part or additional, there will be reinforced learning in this part. And all this called post-training. And after that, you have a very generic, it's not a task-specific application, it's a general model. It's actually pretty general model. You can do essentially everything. So that's recognized. But before, but let's say 80 years ago, right? If you are talking about first BERT, we're talking about at that time, people would really say once you pre-train a BERT on a lot of unlabeled data, you get a capability. You should fine tune for very specific tasks. This one is a general task. In fact, this one starting to be very specific task. Those specific tasks like classification, sentiment analysis, for example. If you have different tasks, you have to fine tune a different model. So essentially, you have many models, small models. Nowadays, we still have specialized models, but a lot of times a general model is good enough, right, to do a lot of things. A general model. But usually at this time, it's much more focused on the special model. It's less focused on the general model. But general model is just the starting point. So basically, that's why it's called pre-training fine-tuning. Pre-train the general model, right? And then you fine-tune to a special. Yeah. And this special model can do. We will see an example about GPT-2 fine-tuning. We'll give an illustration, but essentially, this is about the paradigm, and of course, this one unsupervised pre-training, you just need a lot of tags. You don't need the labels. For the special case, in the traditional setting, NLU, they are thinking about the classification. Then you need the label, right? They are thinking about maybe you do some translation. At that time, at least, you also need the label to train. But now realize what's interesting is you don't even need the labels to do translation because these guys actually can do translation. It's actually a miracle. It's a surprise. I mean, the people didn't know. I don't actually believe people know details how they learned translation, to be honest, even now. But it happens, it just the capability that comes up. So if they may see some pairs of languages, right? But they don't see all pairs. If you're starting to do translation using the traditional view, they will start to think about all pairs, English to Chinese, English to French, right? So but here, you don't need, you can ask whatever, they know they have the same representation. The transformer learns the actual representation of the language, which is somehow a little bit outside of translation. So these are very generic, but traditionally, if you think about different tasks, let's say English, Chinese, you probably need to do specific model, right, or whatever model. Pre-training is on a large number of unlabeled text, and fine-tuning is adapted to very specific tasks. But this one is emphasized a lot in the older models, not more in the more recent models. Okay, and basically this is the paradigm. So yeah, I think I'll go quickly because probably people knows what it is anyway. So pre-training on large unlabeled, whatever this one is basically it says you know the linguistic pattern, you know linguistic pattern. Fine-tuning, sentiment analysis. Later on, we will talk about the instruction tuning. The whole lecture talking about the instruction tuning, that is regarded as also as a kind of fine-tuning, supervised fine-tuning. Those instruction tuning, the purpose is when you do the pre-training of a language model, usually they do not know how to follow human instructions. After instruction tuning, they will know what actually you want from the so they will have the ability. We'll talk about that later. That certainly is important for the chatbots, right? So they need to understand your instruction, following the instruction to perform whatever you want them to do. But you know, the basic linguistic pattern, even all the translation ability, whatever, already been learned from unlabeled text, right? So and why they can learn translation? It's still I don't know, but somehow it does happen. So one fine-tuned on this kind of classification, right? Models will be built because they will know what you want. It's like an instruction tuning. You know actually they want is positive or negative, right? So you tell them what you want essentially. After pre-training, it's already understand the language, right? They know something are probably connected, something are not the same, but they don't know what you want, and this is fine too. And this is much easier. You can use much smaller data because they already learned basic representations here from the pre-training. So pre-training in some sense is learning basic generation representation. So pre-training, I'll go quickly get, yeah, so learn large scale, adapt for specific, learns general language, learn specific features, develop a robust representation, and this turns out to be very powerful, and learns basically learns really what you want for your target. All this instruction tuning, post-training, right? Instruction tuning, all these RL, reinforced learning. Sometimes people say they are just extracting what's already there in the pre-training. The pre-training just don't know what to do with those knowledge, but once you extract those, they will starting to be more explicit. They know actually what you want, so they know what is the right thing to do, and that essentially they have these particular targets. They will be able to optimize. Pre-training provide a language foundation, fine-tuning customer for the target. So that's one. Yeah. And of course nowadays pre-training, because my understanding at least the pre-training the text has been exhausted, so it's more the current is more towards post-training. But this is not the traditional fine-tuning. Traditional fine usually use a very small corpus. You have a large pre-training, small corpus, right? Now, when you really want them to gain more ability like reasoning and so on, they need a larger corpus. Even for the post-training, a lot of shifts towards that, but they are getting larger and larger data sets for those. How to pre-train? Right, so basically, encoder only. So we'll talk about this master language model. And next sentence, this is from the third paper. And later on, people drop this more, but this one is important. This one actually have a revised nowadays. A lot of nowadays, if people talk about the diffusion language model and so on, they have one part is the master language model would be related to that. But we will not go over that. So we will talk about diffusion, but we will not talk about diffusion language. Okay. But this is highly related. So this one comes up with a little bit revision nowadays in a slightly different context. Decoder only, of course, just the next token prediction. So that's the simplest thing. Master language model, there's some complexities we will see. Autoregressive. And two things, right? So one thing is, of course, they are objective different, training objective. This one is master language model, one is next total prediction. The second thing is the attention is different, right? I will keep mentioning this. Attention, this is a bidirectional attention. This is unidirectional. It's a causal attention. Encoder, decoder, of course, you just, there are the encoder, there's a decoder. Then you have to do some kind of related to this kind of ideas, but they use very related, slightly different ideas. If you look at how T5 is trained, right? Decoder is the same as this guy. So basically, different encoder that while do the pre-training, right? Different encoder and the decoder, they have different target. Decoder is the simplest. Next token prediction, we all know. So we will talk more probably, and we already know that how to do that. So we don't spend time on that. We will probably talk a little bit more about the BERT, which is a master language model. And again, as I said, master language model has a revision because there's a highly related to the diffusion language model, which is a current topic. People try to investigate that, and this is one, close related. So we will probably talk a little bit about that. So basically, this is a BERT, right? BERT associated with the encoder only transformer. It is pre-trained on unlabeled data using so-called master language. What does that mean, master language model, right? Essentially, you have a sentence given, right? You are masking some. Thinking about, because we mentioned that there's also something about this one with the denoising autoencoder in some way, at least at some level, right? This one mask, essentially, you can say add noise. You have randomly flipping this to a mask token. This is like adding noise, specific type of noise. And then you say, can I recover this sentence from this, right? So when you recover, you should recover all these mask tokens. So that's basically the task. It's somewhat like a denoising autoencoder, because all other tokens know, right? So you just send out all other tokens. So essentially, what you are BERT encoder, you are coming out with the masks. That's what exactly you want to predict. And they put additional tokens. This is a sentence starting. This one is a sentence end. So each sentence they try to put a symbol in the beginning and a symbol in the end. This one can be used to extract representation, because this is bidirectional. If you remember, everything like this kind of tokens are all attended to everything. So you can use this guy or that guy. They all see all the sentences. They are not seeing just before, right? If you have a GPT, you probably have to put the representation in the end, because that end token will see everything before, right? But here this is what it is. So master language model is like adding mask as noise. That's why it's a little bit also related to the diffusion model, because diffusion model is adding noise, right? It's a slightly different way to adding noise. And this this mask that basically denoising autoencoder. Think about that. In pre-training, a BERT uses a masked language model as objective, and then you just using transformer, and then you are done. So that's it. There are two special tokens. They can be used to extract the representation. If you want a single token representation instead of a sequence token representation. When we say, right, we have a transformer, we can use cross attention with a sequence tokens. But if you say, I just want to have a classification F, usually you want a single token representation. And this one can be used for extracting that. Random subset is by mask, right? So basically, it's like you're adding noise. The noise is flipping to mask. And then transformer is trained to predict original tokens at these positions. And yeah, so that's all. Basically, that's all it is, right? Because transformer, if you remember, the token, each token is aligned. So in the end, you can just output a logic of this guy, and that it will produce. Yeah. This supports bidirectional. Also, another thing is what actually that's why maybe I'll just quickly mention. So why this one is relevant for diffusion, whatever, right? So because the mask can you can simultaneously predict all the masks. Okay, so this is a parallel decoding. If you're thinking about if let's say I put a mask in the end, right, just end, then you can parallel decoding. So this is different from the autoregressive. Autoregressive, you cannot do parallel. Yeah, this is why people get attracted to this idea. It's basically through that bidirectional one thing. I don't want to focus that too much, but mostly people focus on the parallel decoding ability of this kind of mass language model or diffusion language. That's why that's starting. But you know this one does support a bidirectional, right? So I think I need to mention this parallel. Maybe I was just adding another sentence to say all the masks can be parallel decoded. So what are drawbacks, right? Drawbacks, of course, people now putting more time on this, but it's a special form. It's not in the original form of mass language model, but in a more revised form. Yeah, so we will talk about that. What is the challenge about this a little bit later? But let's say what is this is a pre-trained. So you're using that objective. There is next sentence prediction. We will skip that. But let's say the mass language model prediction, and you have the hidden state. Let's say you just picking this, right? Actually, it doesn't matter which one you pick, but basically you just pick that as hidden state because they see all these tokens, and you have a task-specific head. And let's say classification or classifier, you just have MLP, right? Or just a linear projection. Then it's output that becomes logics. Logics becomes a label. So that's it. But you can do that other head. Other hand, usually heads to say what kind of problem you are interested in. That you can have a regression head basically instead of output the logics, output a real number, and so on. But basically, this one is a small neural nets typically. Okay, this head, the MLP typically. So that's about it. In fine tuning, the pre-trained BERT is adapted to downstream just by you can freeze that, or there are two ways to do that, right? One way you can freeze all the BERT, and you just update the heads, right? So this one treating as input. The other way you can simultaneously update the BERTs as well as that. Both can be okay, depending on the applications. So you can do, but essentially this is a pipeline. The pipeline you pre-train a BERT, you learn this representation, you are keep training on a specific task. Okay, let's say sentiment analysis classification task, and then you have the final token is fed to the head, and you can label the data, and when you train that, you can either just train this head, or you can train the whole thing, or yeah, you can freeze, you cannot. Either way, it's fine. BERT is rather a small model. Nowadays, I mean, used to be considered large. That is probably 10 years ago that considered large model, but nowadays it's a very small model. So it's very easy to train. So, so what is the disadvantage of that? Yeah, so I think it's mainly if you look at this mass language model prediction, there are some inefficiency to that. That's one thing, because you are not looking at basically, let's say you mask 10% or 20%, right? Essentially, you are thinking about your information from the label is 10%, right? So that's one. The other one, there are various other issues to do with that. But so mass because how do you separate sentence, right? How do you separate your attention and so on. So these various issues with that. And how do you apply that, right? If you want to say apply to just for the NLU, just looking at this prediction, this representation is okay. But if you want to say I want to do more, that's also a challenge. Unless you switch to a diffusion language model, then that's a slight matter. that is a more modern revision of this kind of model. So encoder decoder model, right? Encoder decoder, this is the same. You have a masked language, or they have a variations of that. If you look at the T5, they mask a span, a consecutive tokens, span of tokens. They are not so much a single tokens. They on T5, and this encoder, that decoder, you just auto regress, right? Basically. So that's yeah. That's about it. T5 are pre-trained using denoising autoencoder. Again, it is still kind of a denoising and corrupted, and the encoder process the corrupted inputs before the auto-regress generate. So decoder can do a next generation prediction, can also generate this thing. But basically, basically this one. I don't think this architecture has been used. Now I think this one, I don't know. People keep investing. Maybe at some time people realize that this kind of architecture is interesting. As I mentioned, for the BERT master language model, there's a revised interest in a different context. This one might be, but nowadays really you're just aware of what's happening there. But I don't see that being revised interest in this. So this one definitely is not it's a. I won't say it's a dead end, because maybe a few years later, some people think there are some advantages coming back to this. Right? But basically, this is not something people do nowadays. Encoder decoder, right? So fine tuning, and it depends on what you want, right? You can use the encoder to do that. You can use encoder, right? Or you can use a decoder. So this is actually pretty flexible from this. I can do encoder. I can come in like a classification hat, just like a BERT is how BERT is used, right? I can discard the decoder, right? And I can have a decoder, right? And output, right? So basically, this is because decoder. Remember, we all know, encoder decoder include decoder, so they can do next token prediction. So you can always using the prompts as a way of using decoder to output. Right? So there are different ways to apply this. So it's actually flexible. Encoder decoder fine tuning inputs and decoder. This one we just need to aware of. We don't want to put too much emphasis on this. Classification, you can do the simple task just using the encoder, or you can use the decoder as well. Depend on how you want to design these are fine tuned. Okay, so that's about it. So now let's talk about decoder anomaly. Decoder anomaly, of course, is the mainstream nowadays. It's the whatever, right? So, and you want to predict the next token. It's a GPT decoder, next token prediction, then you get that. So, and the pre-training is pretty simple. This is the target. That's all, right? So there's no master language model. In decoder anomaly pre-training, the model is trained to predict the next token in an auto-regressive fashion. Of course, disadvantage is that when you do the decoding, you have the one at a time. People have basically people have created some other creative ideas, try to do better than this, but those are very specialized topics. If you don't do that, then it's just one at a time. Attention map is unidirectional to the left. Right, attention map is always unidirectional to the left. Basically, it's a causal attention map. This object is enabled to learn long context, and it's also very efficient. The efficient at a different level, right? Efficient in the sense of it's simple, and whatever you feed that, it can train on that. It doesn't really. You don't need to worry about into sentences. You don't need to worry about say you have to do the masking and so on. You just always and also the training is parallelizable, right? Another thing. Large model can be trained. So training is parallelizable is one thing which is useful, right? So if you want to fine tune a decoder only model, what you do? You start with a decoder, right? So let's say you want to use that for classification, right? For classification, there are several ways to do that. One way you say, let's say you say, okay, for example, this is a sentence. This sentence you want to classify this sentence to say, I mean, this one, of course, when you look at this, is probably just it's really just it's a writing, it's a generation. But let's say there's a sentence you want to classify to be whether it's belongs to whatever classes. Then what you can do is you can use this, right? You do not want to use the starting of sentence because you know there's nothing. Here, causal attention means this guy has all the information of the whole sentence. So the final representation of this coming to with transformer hidden state, right? There's a model, you always have this D model, recall, representation, vector representation. And that one you can put a classification head and use that classification. Another one is usually you do an average of all these heads because each one output one of this D model, you can do an average of that, then use as a head to do classification. This one matters because you know classification heads still are useful nowadays, even in the language model era, because when people do reward training, we probably will do something like that. To do the reward model, basically when you do reinforced learning, right? Reward model, they want to say, given a trace, a sequence of text, what is you want to give it a number. The number is say 1 is good, or 0 is bad, and then something in between. Essentially, this tells the reward. And those are usually you could either using this or sometimes people train a reward model this way. Basically, you come out with a hat. And so this one is a pretty one way to do that. By using this special hidden token aligned with hidden representation of the last token. Another way to do that is just treating that as a prompt. You just ask that, so what is the, what is the class? What is the sentiment of this, right? And then you have to produce either positive or negative. And then you want that to be positive or negative. So essentially using the treating as a prompt, using the sequence generation ability of a large language model to generate the final answer. So these are two different. If you think about this one, you have a special head. It's a different model. This one is kind of the same model GPT, just force them to give you answer. When you give an answer, you can also do a filtering to say this one you ask that has to be either positive or negative. Let's say you ask that you just looking at these two tokens, right? Just check there because you have logics. So you can just normalize the answer that you have the prediction. So basically, you either put another hat. This is optional by using the embedding of your sequence, your token or your average of your token, or you're just using the keep decoding. So then you don't need this. You just keep decoding until at some point you're asking that to either positive or negative token. Okay, so both ways are fine, but nowadays I think people shifting towards the latter way, right? They want to shift because that makes things a little bit easier. So positive and negative. So pre-trained causal encoding adapted to the downstream task, and this can be quite flexible. Right, you can just using the prompts, and or you can fine tune a bit about this model. And the model takes a prompt and generates text autoregressively, right? And you could optional task, as I mentioned, it often attach the last token's final, right, to predict the decoder. That's just what I mentioned. But it could also put an average. You could also use the average of these tokens prediction. That also you see figure it out. Or you just continue generation. So this one is one way, right? Or continuous generation is another one. So you have two ways to do this kind of things. I will talk a little bit about the known models and the model size and so on. So about this encoder decoder model and the decoder omni model. And the decoder only model, I probably just talk about GPT. Of course, now there's many more other models. So BERT, right? So it's regarded as pretty small. Base model is 100 million. At that time, it's very large. This actually is a pretty revolutionary paper. This is the first demonstration of this capability of pre-training, fine-tuning paradigm in language. There are also something going on in the vision, computer vision, pre-training, and so on. Like remember, we do this contrast learning, right? This can be regarded as a pre-training for computer vision, right? Contrast learning work. We talk about that. And here is contrast learning is unsupervised, right? So here it's a representation learning for the for this and for language, and certainly they have this mass language model training target. That's one contribution. Next language prediction, but mass language, and this one also used by other means, including current diffusion model, including computer vision. There is a mass language model for the computer vision type of encoder learning or representation learning. So this one is highly inferential, and especially the way it's a training objective. Roberta, I mean, this is encoder decode. This one is just using a little bit larger. You know, it's not too much. Conceptually, it's not much, but this one used a lot. People, you know, this one is they are undertrained. The claim. Roberta just make it more better trained. Okay, better trained. So basically, these are the models. There's deBERTA and so on. So there's a few BERTAs around that time. Yeah, deBERTA. Yeah, so basically. But we don't want to talk too much about that. Basically, you know, this one you can still use. I don't believe they are still keep developing these kind of models. These are pretty much always there. BART is encoder decoder, right? So it's NLU plus NLG, the usage. And according to traditional, right? So and this, I mean, if you look at all sides, now it's a very large, and the T5 is a Google's model. This one is can be pretty large, 11 billion. Even by current standard, it's not small. I mean, it's academic budget will be probably usually, you know, it's 8 billion, 11 billion is probably you can do in academics, but generally, yeah. This one I think is push this encoder decoder to the too much, essentially to what it is, right? This one starting, I don't think people is continuing this a lot. Maybe in some special applications, but generally we are not. As I mentioned, you know, this encoder only have some revision. The revised interest because diffusion language model, because their ability to simultaneously decode all the mass tokens. And these guys are not. Yeah. So yeah. So basically, one reason, of course, let me comment this, right? So if you think about the encoder decoder model versus the decoder only, right? You can clearly see advantage of encoder because they are trained with a different objective. They are actually have a bidirectional attention, right? So they seem to capture more from bidirection. That's why I think Google's starting to work on those before. They think, but there's a very crucial drawback. Even it works, right? And there are a lot of other issues with that. But there's a crucial drawback is if you have a model size, let's say whatever, say 1 billion, right? If you have a decoder only model, 1 billion goes to decoder. Encoder decoder model, it's 0.5 billion goes to encoder, 0.5 billion goes to decoder. So essentially, your model, because they are different, they only restrict for different purpose. So your model, in fact, model size is not too large. It's not only become more complex, but the capability becomes smaller. People do the study to say, okay, let's say do the encoder decoder model, encoder versus decoder model. Let's keep the model size the same. How do you compare their performance? Let's even for classification and so on. Seems the model size matters more basically than whether you have decoder. So therefore, all the complexity of encoder decoder doesn't seem to pay off because of you have to split the model size. Decoder omelet model, it's pioneered by OpenAI, right? So GPT-1 is about the same time as the BERT, but it doesn't draw attention at that time. It's a pre-training using autoregressive because there's nothing particularly new. If you think about it, just BERT, right? So they have a new objective function, master language model. Then it's a bidirectional attention. So therefore, you have more powerful in some sense for that model size. Bidirectional attention gives you some advantage. So GPT-1 doesn't have a lot of advantages over BERT. GPT-2 starting, it's open source, right? So we have those models. They're starting kind of interesting in the sense they talk about the few behaviors. One is that they can do much better writing than earlier models. Earlier model, when we say earlier models is like LSTMs and so on, right? So before this, I mean, this one is the first one is a transformer architecture, pre-trained, large scale, so that they can actually doing the language, and they realize that this one actually does. And they also see a little bit starting to look at the NLU problems, because at that time, these people focus more on the although they show the generation ability, more focus more on the NLU, so they look at the so-called zero shot, few shots. You just give a few examples, they will be able to actually do the NLU well. So essentially, this one has already shown something interesting. It's a little bit beyond what BERT can do in some sense. GPT-3 is a kind of separation point. This moment is really far beyond the BERT, and this is where actually people starting to draw attention to after this paper, right? Starting to work on other people. I mean, besides the OpenAI, like Google, like Meta, and so on, starting to put resources into the decoder omelet model. This one they demonstrate. This is the NeuralSpecs paper. It's a NeuralSpecs paper. So it's a massive scale, right? And strong in context learning. This one is still not the ChatGPT. ChatGPT requires additional steps, which we'll talk about later. GPT-3 plus instruction tuning plus RLHF is ChatGPT. Yeah, they do publish paper actually on that. Instruction GPT, which is basically the paper associated with the ChatGPT. GPT 3.5. So basically, this requires post-training. These are pre-trained model. And these models, people starting already use that. Actually, there are companies built around using prompt engineering with these kind of models for writing, right, and so on. So methods play strong in context learning across many tasks. So this is something. Then GPT-4, yeah. So then you add more, right? Multimodal inputs, right? So people now put a lot of time to multimodal. Again, you need the encoder now. Once you're starting to talk about the multimodal, there are some there are more complex designs. There are actually various designs, but the one simple design is you need the encoder from image and put that into language. So using cross attach, right? Something like that. Okay. So this is and reasoning now it's become important. A lot of people doing reasoning models. Clearly, OpenAI have the O series, and then they later merged into GPT-5 and so on. But essentially, reasoning and instruction following is there. It's actually instruction following is a 3.5, right? It's in between GPT-3 GPT-4, and yeah, and a lot of other issues. So, and of course now it's developed, but basically we just stop from there. And clearly there's key part. Each time we discuss a little bit more, like this few shot learning. We'll talk about the in-context learning. Is what emphasized here. And they realize that this time is a very general model. Once you can do, they actually can across many tasks. It's a universal model in some way, right? You can do translation. You can do text writing, you can do whatever you want. You can do classification and so on. So it's kind of starting to building to be universal mode. And certainly gradually now it's demonstrated more, right? So nowadays, yeah. So that's around that time. Okay. So these and I think at this point, people gradually at that time I think people starting to pay much more attention to the decoder omni-mode, and they try to work on that. And nowadays, of course, they stop dominant. So basically, yeah, basically this is a picture. I think that's about what I want to say about these models. Eventually, next few, I believe next time we'll talk about the instruction following, instruction tuning, and then we'll talk about mostly focusing on this, right? Decoder omni model in the rest of part two, right? Part two lectures. Next time we'll talk about the instruction following, right? So this instruction tuning, and then later on we'll talk about the RL and so on. But before that, one thing I think I want to say a little bit is the Hugging Face. Hugging Face is what we are actually will be using. I mean, in the open source community, everybody is relying on Hugging Face to build this kind of models. Because Hugging Face has this transformer library, which is well written, and there are a lot of models. A lot of models put in there, so you can plug in and using their interface and so on. So I'll talk a little bit about the Hugging Face. We already know in the last lecture we have to have the packing token, right? We have attention mask, right? So here is what usually you get for the attention mask. When we talk about the internal representation of attention mask, is either 0 or negative infinity, negative number, like minus 10 to the 9, right? So if you recall that, that is adding to the logits, making the corresponding probability close to 0. So here is what you actually represented, because you don't want to say negative 10 to the 9 as your attention mask when you have a user specification. So user specification is attention mask 1 and 0. 0 is a padding token. Padding token is where you shouldn't try your attend to, but you want to keep these lines to be the fixed lines so that you can do training across batches of different size, sentence size, right? So if you recall this is the purpose. And basically, these are context tokens. Mask value equals 1 means this one needs to be attended. This padding token says you do not attend that. And internally, if it's a decoder model, you also have causal attention mask, right? So that one we know. But this one is padding attention mask, which you specify. So basically, it's a 0, 1 in the Hugging Face interface when you do the attention mask. And attention mask is 0 means padding, 1 means valid, and then essentially, if it's encoder, right? If it's 1 mask, internally it's 0. Basically, you don't add anything to your attention, right? So and here it's if it's decoder, then you have to have causal as well. Causal, then you have 0. Otherwise, it's a large negative number. Basically, this is the attention mask associated with a Hugging Face. Now let's look at what we can do with that. The code is already there, so it's basically the same code which I illustrated. So if you look at the notebook, the code, it shows you a GPT-2 fine-tuning example. This fine-tuning is for text generation. You can also fine-tune GPT-2 for classification using 2 methods, right? One method adding a special head. The other head method is just continuous generation until you ask them to output the class, right? So if you recall, But here is just generation. Host stuff other models, data source, we will fine tune on this one, right? This is again, this is an open source book. Yeah, so basically you just have and just see how it's starting to write. I think we did something like this. I don't remember if the problem is the same, probably not the same, maybe the same, but for the LSTM, right? But this one is on a pre-trained GPT-2, so it should do much better than whatever you see with your LSTMs just trained on that data. Hugging Face data for tokenizing, which we have already seen the tokenizer because we did download the tokenizer from Hugging Face. GPT-2 model for text generation, right? So, and Hugging Face trainer for fine tuning and generation. So yeah, so basically we will shift to the Hugging Face trainer, which is a little bit easier. Later on, we also try to explain some other concepts because we will have one class on the resource efficient fine tuning, which involves some additional in the Hugging Face to say when you have a limited GPU, how do you train a larger model? So then you have a so we will just using this this trainer which support all kinds of this kind of with a very simple format. So you don't need to write your training rule. In PyTorch, we write our own training rule, right? If you use this one, they already written the training rule for you. You just pass all the parameters to the train. So we compare this pre-trained model, right? This is just GPT-2 without the fine-tuning. You can see what they respond, and then you fine-tune the model, right? And you say after fine-tuning, basically you have this book, right? So you just train for one, I don't remember, one iteration, so 2 iterations. Then you will fine tune it to this book. Then they know the content more, and then you can try to ask the generation, and then you can also overly fine tune. Once you start to over fine tune, we will see what happens, right? So we will comment on that. Basically, you train that repeatedly many times. Basically, this is what this is just for text generation. So there are GPT-2. We just use the smallest. I think we could use this, but for the if you especially if you have larger, but at this size, there are much better models, right? So there are quite a number of models around 1B. So GPT-2 is not the choice if you go to this size. So we will use this size, right? Even this size is reasonable, but I believe this is what we use, 172. So it's a small model by current standard. Basically, what you do is the following, right? So you have a model, you have a tokenizer. Basically, this head is yeah, it's yeah. Yeah, so basically this is the next token head, and then that tokenizer. Tokenizer we have seen before. So basically this I don't want to go over too much, but essentially this is what I have. The data set. The data set is yeah, I think we see this basically this one is data, and then you this is more like Hugging Face data, right? So there is a data collator, right? So here I just want to make one comment. Usually what you need, they essentially will put the data, put that into batch and do the padding, right? So this is what essentially they do. And certainly MLM is the master language model. This is for bird train, right? So we are using autoregressive. So essentially you pass this before, otherwise it will do the autoregressive. But basically, this affect your padding. How do you want to pad the sequences? Put that into your context so that they are aligned. Yeah. So basically, this is what it looks like. And general response, I mean, this one we will see before. It's the same thing. We just probably quickly go through. Essentially, just one by one generation, right? Model generate. Yeah. Basically, you you basically you have this one GPT-2 model. You have input IDs, and you have attention mask, and you sampling, and there's temperature. This one we explained before, so I don't want to go through that. But then you have padding tokens, and you just generate your decode. This one generates tokens, right? The token IDs. Token IDs, then you just use token to decode. That's all. This one is handled by GPT-2 model itself. So it's Hugging Face handles this, and then you start to get this tokenizer output, and that's it. Right, and that is actually generated. Yeah, this one is a pre-trained model. How it generates? It's actually generate sentence, right? But it has nothing to do with with the book. So yeah, basically this what it looks like. The door. I mean, yeah, you can take a look. I mean, essentially, because it's a pre-trained GPT-2, it's not the LSTM we dealt with, just the terrestrial train. So it generates a reasonable sentence. Yeah, but it really has nothing to do with it. Yeah. Trainer is pretty simple, so that's why we can shift to these, because I assume you can write a training loop yourself at this point. That is part one, right? Part two, we are focused mostly on the LLM's related stuffs. We are not. There are no need to write another training loop, right? So you use Hugging Face trainer because the sequence generation, you need to padding and so on. You have to do quite a bit of things inside. But basically, you just pass this guy, right? Your training arcs, essentially, you just tell the trainers, and this is basically there are other arguments, but essentially, when you see that, it's kind of reason. But the trainer, you have a model, right? Model is your GPT-2. You have training arguments, right? Data collator, right? So this one is one to the padding, to the batching, and so on, right? That training data, right? They get from this, and then you just do train. So it's pretty simple. You get some arguments which specify your trainer, and then you are just calling the trainer. You don't need to write the training loop yourself, and then you do the training. Yeah. After that, actually, let me see whether it. Yeah, number of apples is 2, right? So right now it's 2 apples. That sample generates. This one certainly is much more connected to the book. There are queens, right? So there's hearts and so on. If you're familiar, that basically is quite relevant. So basically, it means that the fine tuning does lead to some information which aligned with the book. So at this point, you can also check the loss and so on. At this point, it's regarded as better aligned with the book when you do the fine tuning a bit. Right. So basically, yeah, this is output. Right. Also, it's still reasonable English sentence. Right. This is the English sentence. Reasonable. although it doesn't really doesn't not necessarily it's logically makes a lot of sense. It just again it's a fluent sentence. Mostly I haven't checked all the sentence, but it's mostly fluent. And also it's related to the book. Okay, so now overtune, what happens, right? You tune for more iterations, right? Then what you get is the following. When you tune for more iterations, what happens? Then it sometimes it's get let me see. Yeah, it doesn't happen here, but it's actually become a little bit strange if you look at that. Starting not to be like that, right? So yeah, it's also there's a tendency, but it doesn't show that clearly. But you do see that already happens again here. Is that's very typical when you're starting to overtrain a language model. It's starting repeating things, but this one is not as extreme. Sometimes it's even more extreme. I have tried this way in the way, right? So I have tried this way. If you look at and or have tried and I have tried to understand it. So it's starting to repeating things quite a bit. And this pattern is pretty common in this kind of large language model when you fine tune a lot. They try to have this behavior. So repeating something. Once you see that, or whatever, this means you are too much fine tuned. And you can measure. Sometimes you can measure that. We don't measure here. It's by entropy of your general sentence and so on. Usually they're related like loss of entropy reduce. So it's your generation is not as diverse, right? And so on. Repetition is kind of it's kind of an indication of your generation is not diverse enough, and you are losing ability basically. So it does see that here. So basically, this is what it looks like when you try to train a language model, you find something this kind of behavior. Essentially, this means you're too much. Okay. Of course, too much can hurt it. Just focus it's try to memorize your training data or fine tune data. You're not going to really do something. So copy training phrases lose generality, and repeating phrases is a very clear indication of that. The forgetting about what you're learning for training, which is bad. This is always the case when you're starting to fine tune things. This is not only to do with language model, but more generally machine learning nowadays. Forgetting when you're starting to learn new things is an issue. People try to address, or try to mitigate. This is also active research topic. How to deal with that, and there are distribution shifts because you're too much focused on very narrow topic. Basically, it is bad. Sometimes it can be unstable because once you train too much, it's starting to blow a little bit because it becomes very sharp the prediction. So yeah. So practically, you can do a smaller learning rate, early stopping, and keeping high data, and that match to a style, and so on. So to generate that. So that's the general. Once you're starting to do this, there's something you should be aware of. I think that's all. So this just quickly talking about that, and the future lectures will continue to talk about the decoder LLMs. Okay. Any questions, you guys?